Let's look at some applications of circular motion. Let's look at horizontal circles. For example, let's look at a flat circle where the radius is here. Here's our radius. And maybe we have a box sitting here. And this whole thing is going to rotate about an axis through the middle here, like that. So in this case, the forces acting on the box would be the force due to the gravitational pull of the Earth and a normal force from the disk or the rotating platform up on the object. And then if this box is to stay moving around and around in this circle and not losing contact, then there has to be something holding it in the circle. Something has to be holding this box as it goes around and around the circle, holding it in the circle. And so as you say, holding it in the circle, well, it's not slipping, so I would call that a friction force. And it's static friction force. And so that's the static friction force is pointing towards the center of the circle. And so in this case, because the force that's pushing or pulling it towards the center is this friction force, that is the center seeking force. Now let's look at this free body diagram and sum our forces. Since the force in the x direction is unbalanced, there's nothing on this side, then we will have that the sum of the forces in the x direction would be equal to ma. In the y direction, up and down, there are balanced forces. The object's not rising or falling, and so the normal force up minus the weight force down equals 0. So let's take a look at what's happening in the x direction. In the x direction, there is a friction force pointing towards the center. And so instead of any old acceleration, it's a special acceleration. It's a center-seeking acceleration. So taking this further, I remember that the friction force is mu times normal. And we have discussed that the center-seeking acceleration is velocity squared over radius. And then my normal force, though, can be found over here. So the force normal would be equal to the weight. So let's make that substitution. And when we do, we'll have that mu times the gravitational force is equal to mv squared over r. Now, the gravitational force is also one that we've studied, and it's equal to m times g, the mass of the object times the gravitational field constant, 9.8 or approximately 10. So that would equal mv squared over r. Now you can probably see that I could divide by m on both sides, and when I do, I get an equation that looks like mu g is equal to v squared over r. I can solve for v, and v would be equal to r mu g all under the square root. Now what this gives me is the maximum speed of the rotating disc such that the box does not move. Sometimes I jokingly call this root rug. So it's the square root of r mu g. So r is the radius, mu is the coefficient of friction, and g is the gravitational field. So let's look at an example. We've got a flat disk and it's rotating with a tangential velocity of 2 meters per second. We've got a box with a mass of 4 kilograms is on the flat disk at a distance of 1 meter from the center. What force of friction is needed to keep the box moving on the rotating disc? So let's see. So if the box is sitting on the disc and it's moving around and around this axis and the box doesn't slip, and it has a tangential velocity, so that's the velocity tangent to the path that it's making, of 2 meters per second, what friction force would need to be applied to the box? So first we're going to draw a free body diagram of all the forces acting on the box. So if this is my box, there's definitely the earth pulling on the box and the disc pushing back up on the box. And then in order to keep it from slipping out of the circle, there must be a force directed towards the center of the circle. And in this case, it must be friction because nothing else is there to hold it. So when I sum the forces in the x direction, I see that they're not balanced. There's no opposite force of the friction force over here, so that I know that it must be unbalanced. When I sum the forces in the y direction, I can see that they are balanced. The disc isn't rising or falling. So in the x direction, I've got a force of friction static, that one, and it is going to cause a center-seeking acceleration. And then in the y direction, I have a normal force up and a weight force down. So the question asks for the force of friction, which is this right here, which is buried right there. And I think that we've got the mass of the object, and then A sub c is that special acceleration that is directed towards the center, and we have a function to determine that. So let's substitute in. So our force of friction would be equal to m, and then this centripetal or center-seeking acceleration is v squared over r. The mass was 4 kilograms. The velocity is 2. Don't forget to square it. And the radius was 1. So then we'll have 4 times 4, or 16 newtons. Now, the next part of this question is, our next question that could be answered is, what coefficient of friction is needed? So now remember that the force of friction is mu times force normal. And earlier when we were summing our forces, we had a normal force up, the weight force down, and that was equal to 0, which means that the normal force will be equal to the weight. So the normal force is equal to m times g. So now let's substitute that. So our force of friction is equal to mu times mg. So we have 16 equals mu. Mass is 4, g is 10. So then our coefficient of friction is 16 divided by 40, which is 0.4. And remember, mu, or the coefficient of friction, does not have a unit.